everyone, welcome to our webinar. This is Jill Hurston with Synerzip. I'd like to remind you all before we start that I am recording this session and everyone will receive an email from me tomorrow at the same time with a direct link to the webinar presentation and the recording. So right now I'd like to switch it over to Sabu Sankara. He is our VP of Software Engineering.
Thanks, Jill. Welcome everyone, and thank you for taking time from your busy schedule to attend this webinar on this important topic. This is your moderator, Subbu. Some housekeeping announcements at the start. While the presentation is underway, please feel free to enter any questions you might have at any time. And I will try to bring up your questions at convenient times during the presentation so that we'll make it fairly interactive. If you cannot answer any questions, in this forum, someone from Synerzip will follow up with responses. So please make sure that you get all your questions into the system by tapping it at any time as the slides are being run. And now over to the topic. The topic on hand is real-time with AI, the convergence of big data and AI. I know these are all hot buttons in today's technology world. And we will learn how to work with all of these or any of these and how they all fit together. Now, introduction to our speaker, Colin. Colin McNaughton is an accomplished technical leader. As head of engineering, Colin is responsible for leading core development team and still maintaining an active role in development. And he holds many patents in fault-tolerant computing techniques, business process modeling, and serves on standards working groups. His most recent creation is the X platform, combining messaging, compute, and data using one simple application framework that we're going to learn a little bit in this presentation. Colin doesn't compromise on reliability, scalability, mission criticality, etc. So he's a very well-accomplished technical leader with a deep technical expertise. He tackles problems that are difficult to solve. Today, Colin is going to talk about AI and machine learning and how it affects big data. And once again, I encourage everyone to type in questions at any time, and I will bring them up appropriately. And over to you, Colin.
Thank you very much, Jill and Sabu. So I'd like to thank everyone else for joining as well. So Sabu did a pretty good introduction of who we are at Need Research, but just to recap, we're the creators of the X platform, and it's really a platform that holistically tackles front-facing operational applications that are transactional in nature, and it does that by combining and handling messaging, data, and compute in one platform. So we focus very much on transactional front-end systems, and we'll see that will be most of my focus in the talk today when talking about how that intersects with machine learning and AI. So our agenda today is talking about where big data and machine learning really intersect, and the main point is that the more data you can harness in your transaction processing plane and in your backend, the better machine learning models we can create. So we're going to talk a little bit about just what it takes to build machine learning models and why they're so data hungry. And then go on to focus on what it takes to bring a developed machine learning model into production, into applications that are doing transaction processing, meaning that they're updating a lot of data, but also now have this large analytical workload running to collect the data that we want to feed to our machine learning models. And we need to do that within an SLA that is responsible enough for these front-facing user applications. And to tie it all together, we'll be looking at sort of some of the architectures and architectural approaches we can take actually bring these into production. So we'll take a look at a fraud detection use case using machine learning and see what sort of performance we can expect by employing the right sort of architectural techniques. So big data and machine learning really are married together. They go hand in hand before a machine learning model even hits production. So from a point of view of training our models, building them up, they're really data hungry, and our organizations have been amassing a large amount of data over the years. And machine learning is giving us a new way to bring or provide value with that data by mining it, transforming it into a sort of normalized form that we can use to train a machine learning model that gives us some sort of predictive output that we're looking to achieve. So the training phase, tends to involve looking at a massive amount of data, cleaning it, normalizing it so that we can feed it into a model. And then beyond that, we need additional data to validate that our model is actually producing the results that we're looking for with the level of accuracy we're looking for. So that's not as much our focus today. I should say sort of here at the top that I am not a data scientist, but what I do specialize in is transaction processing and combining analytical workloads with operational workloads. So what we're really going to be focusing on today is what it takes to bring a machine learning model that we've trained already into production and how to do that without impacting our transaction processing systems. So the main focus here is that the more data that we can assemble in real time in our transactional applications to feed as inputs to our models, the more accurate those models can be. Our data scientists want to leverage as much data as they can to produce accurate outputs in a machine learning model. And this really comes down to being, what's come to be known as an HTAP or HOPE problem, these hybrid transactional analytical workloads where we have a lot of data coming in the front end that is update intensive, but now machine learning trying to do analytical workloads on them, which are very read intensive. And those problems are hard to solve because when we're trying to read a lot of data in a consistent fashion, it tends to block out our ability to update that data. So we'll look a little bit at that. And finally, machine learning models, they tend to degrade over time. So it puts a bit more demand on us in terms of agility, in terms of wanting to be able to develop new models, get them into production quickly. So we want to look at loosely coupled agile architectures like microservices to achieve or to bring machine learning into our transaction processing plane. And there are some challenges with those more loosely coupled architectures just in terms of the amount of data we're looking at and how much data we have to slosh around. So we'll take a look at that as well. So I've been talking a lot about transactional applications. So just to give us a sense of the types of applications I'm looking at, financial trading like risk analysis engines. I want to keep track of my exposure real time. IoT event processors where I've got large sensor networks of data and I want to in real time be able to ingest that data and also look at historical data to anticipate problems before they occur. Credit card processing, the example we're going to look at the end of today's talk, I want to be able to, as authorization requests are coming in, look at a lot of information about the card holder, a lot of information about the merchant, and do that in a historical fashion. So look at a lot of historical data to determine whether a transaction is fraudulent. And so the list goes on. E-commerce, again, personalization engines. I have a lot of data about a customer to offer, provide a good offer to them. So I want to be able to amass a large amount of data, feed it to a machine learning model, and get a response back to a user in a time where that output is still valuable. So I don't have a lot of time to actually come up with my result. So before I get into just talking a bit about the machine learning workflow, Subbu, any questions so far?
No, not at this time, Colin. You can continue. And I encourage audience to type in questions so that I can pick it up in the next iteration.
Great. So In case you're not a machine learning expert, kind of like me, I just thought we'd talk a bit about the life cycle and workflow of machine learning. So we touched on it a bit before, but initially when working with big data and machine learning, there's a data acquisition phase where I'm trying to pull together various pieces of data, both with inside my organization and outside, to try to identify the pieces of data that are going to be most relevant to training my model to predict the output that I'm looking for. And that's known as feature selection. So feature selection is really the process of just identifying variables or pieces of data that I can feed to my model to help it achieve the result I'm looking for. So if I look at fraud detection or credit card fraud detection, for example, looking at a user's first name might not be a very good predictor of whether a transaction is fraudulent, but looking at the amount of a transaction and how much that differs from past spending history might be a good feature. So once I've identified these, I need to train my model, which is pulling in a lot of historical data or data that I've captured and normalizing that into a vectorized form, just a set of doubles or floats that I'm going to feed into the model as its inputs to get my output. So once I've identified the data, I need to amass it all together to train my model and make sure it's doing what I want to do. And then finally, once that model has been identified, I need to figure out if the data that I did offline, maybe using batch processes, I can actually get that into production and assemble that data in real time so that I can produce the result that we're looking for in a business meaningful time frame. So what we're focusing on today are really the production aspects and what sort of features we want to be able to look at and assemble in real time. And the final step that I won't touch on too much today is just making sure that we've got enough visibility into our models running in production to make sure that they're not degrading over time and are still producing the result that we're looking for. So I'll start. Yes.
So we have a question from Rajesh. Is this a schematic for supervised or unsupervised learning?
It's for supervised learning. Well, it actually kind of applies to both. For us and for the purposes of today's talk, it really would apply to both in terms of bringing a model to production. Once it gets to production, you're really looking at just a set of inputs into the model that's going to generate an output. So, but again, me as not the data scientist expert, it's not really my area of expertise either.
Okay.
So hopefully that answers the question well enough.
Right, please continue.
And maybe it'll become a little bit more clear as I talk through some of the feature selection pieces. So the feature selection process, like I said, it's all about trying to determine from all of the data available to me, what data do I want to look at to get the answer I'm looking for. So if I'm trying to train a model to predict home sale prices, for example, things like zip code, things like number of bedrooms, stuff like that, those are likely to predict the median sale price of a home that I'm selling. And so the question is, if I'm trying to build that model, can I get accurate enough results from the data that I already have available to me from my front-end transaction processing system to produce that result, or do I need to pull in more data? So do I have the infrastructure available to assemble all of that data that I need, that my data scientists are telling me is going to produce a better predictive result? And that's where it really comes down to a big data and real-time problem. The more features that I can get access to, the better my models are really going to be. And in a lot of cases, this is looking at historical data, which tends to explode the amount of data that I need to look at. So if I've got an SLA and I want to get a result back to a user in a couple milliseconds, how do I pull all of this data together in a time frame at the scale my business needs to execute at? So even if I've trained a model that's 99.99% accurate using batch processes offline, can I do that real time in production? And as machine learning and model development is a very iterative cycle, like we saw in the picture before, how easy is it for us to adapt our applications so that we can include more data easily and in an agile fashion as our businesses evolve, and as more use cases come online, or as our models evolve? So yes.
So we have one contextual question here from Carl, who's asking, can you use or combine some kind of clustering analysis to help with feature selection?
Not sure I fully understand the question, but I think what's maybe is being asked is, can I do something like a map reduce to collect the data features? And if that's the question, then yes, you can. And we're going to look at how do I pull together data from disparate sources in real time. So by breaking an application up into smaller pieces and developing an orchestration pattern to collect that data, that's exactly the sort of approach I'd recommend, and we'll be taking a look at that.
Okay, very good. Thanks.
So looking at features and just why it's a big data problem, looking at our fraud detection example, generally not all the data I need to feed to my model is coming in a particular request that I'm processing. So I gave the example of the amount of a transaction before. That's probably not going to be particularly useful in making a predictive output about whether the transaction is fraudulent or not. But related to the amount is looking at that amount with respect to a customer's past transaction history, or what similar customers might be doing at a particular merchant in terms of the amount of the charge. If I can look at a user's entire spending history, for example, have they purchased from this merchant before? If so, it seems reasonable that that would be a useful predictor of whether a transaction is suspicious or not. Locations becoming increasingly more relevant. If I see a transaction posted from San Francisco at a point of sale terminal, and then a minute later something in New York from the same card, that transaction is probably going to look suspicious. So this is not just one data point, but it's looking at a bunch of data that's relevant. And we want to do that in real time. So one more example, a personalization example. If I'm trying to do product recommendations, if I can keep track of seasonal interests, for example, this example of Jane who goes snowshoeing in every March and ends up on my website, maybe I want to expose offers about snowshoes if she's shopping in February. And being able to keep track of what past behavior has happened in terms of products that have been surfaced to my user that have generated interest. I want to be able to incorporate that. So looking at past history is a big and useful ability, but it means that I'm going to be looking at a lot of data, and I need to do it quickly. So with this problem of trying to look at a lot of data and doing that in applications that are also updating and adding new data, what sort of problems do we need to worry about when we bring one of these models to production? So these are front-facing operational systems. So I need my transactional systems to perform and perform at scale. As my business grows, as I'm successful, I need to ensure that my solution is going to be able to expand to accommodate additional capacity as well as new functionality as my business is evolving. So there's an agility aspect here too. I want to be able to very flexibly change not just my business logic, but also as we mentioned before, be able to keep my models up to date as they're degrading over time. And as my traffic patterns change, I need to be able to very quickly deploy new models with low risk to my organization. And as these are front-facing systems, high availability is really a must. High availability and reliability. I can't have any downtime across process, machine, or data center failure. So if a machine goes down, I need to be able to continue processing without interruption or any data loss. So these are sort of the non-functional concerns that we need to make sure we have covered when we're looking at a solution to bringing machine learning to production. So looking at what that architecture might look like, this is an example that should be fairly familiar to everyone of an architecture that is sort of typical for doing transaction processing. This is not really a model that I would recommend because it won't really scale to a point. But the traditional model would be to launch my data into memory, a data grid, maybe still on a disk in an RDBMS, and achieve scale by launching a bunch of my transaction processing instances, which gives me high availability. Any one of those instances can go down, and another instance that can take over processing where it left off. But this one fundamentally has scaling issues because if I want any instance to be able to process a particular transaction, I've got to lock that data while I update it. And if I want to assemble a bunch of data, all of the data that I'm looking to feed to my machine learning model, and I want to do so in a consistent fashion, any one of these instances needs to lock that data, which would prevent another instance from updating it. So it doesn't fundamentally actually end up scaling. It only scales to a point. Eventually you get bottlenecked on the data layer. And that's the HTAP problem that I was talking about before, that fundamental disconnect between the ability to do updates and analytical workloads on the same data that's changing rapidly. So you might be familiar with ETL workloads, extract, transform, load. That was the whole idea of being able to try to decouple update-intensive transaction processing with doing analytics. And that's a solution that has worked in the past, but is not nearly real-time enough. So this is a architecture that really won't allow us to scale out and collect a massive amount of data for machine learning in real time. To really create a scalable architecture where I can look at a ton of data, no matter what storage technology you end up using, you've got to think about partitioning your data. So if we model this picture as a single application that is managing some customer data, if I partition my data, I can break out my customer data across multiple partitions. And that way I can actually achieve horizontal scale without two processing instances conflicting with each other from a contention point of view. So now I can have customers, say, with last name M here, and customers with last name F here. And I can continue breaking up my customers as wide as I need to without them having any contention on the data. So as long as I have a routing strategy in place where I can send my request to the correct instance, I can now in parallel scale as wide as I need to go. And so an architecture like that will scale for you, but it's not going to be ideal for the types of big data problems we're looking at. Because even if I partition out my data, if I need to assemble a lot of data about a particular customer in a request, say its entire 2-year transaction history or something, having the data separated from the processing, the one that's going to do the analytics on it, means that I've got a fairly long network round trip to go and fetch all that data from whatever data storage technology I'm using. So for example, if it takes me 10 milliseconds to retrieve that 2-year transaction history, this processor's throughput is effectively limited to 100 requests per second. And that may be fine. I can just scale up and add enough processors to achieve my total target load, but it's not particularly cost effective. So if we want to really supercharge our transaction processing, our ability to do updates and reads as fast as possible, we want to consider an architecture where we're co-locating our data and function together. So whether it be a technology where we're sending function to data or bringing the data to our functions, co-locating data and function really improves our performance of our applications, because now when I'm looking at 2 years of transaction history, I can just do that in memory. So my data is right where my processing is, and it's as easy as doing an iteration through that. So instead of milliseconds to get my data, I'm now operating in microseconds, which brings my transaction rates up to, the tens of thousands, hundreds of thousands of transactions per second. And that's really important because in terms of scale and utilization of hardware, that brings down the cost. My bottom line comes down tremendously if I don't have to scale as wide. The only problem with an architecture like this is that if the data is held in memory with a particular application instance, if one of these application instances dies, I'm going to have a high availability problem and a reliability problem. I might lose data. So the final piece of the puzzle is to make sure that we are replicating updates to data to some sort of backup instance. So my data will be co-located, and as transactions are happening, I'm streaming updates to a backup that's ready to take over in case an instance dies, whether that be process machine or data center failure. So with an architecture like this, where you can bring your data in memory, you can really scale and use your hardware most efficiently. So let me just stop there, see if there are any questions.
Yeah, great. Good timing, Colin. So we have a question from Jen who's asking, what are the typical, you talk about massive amounts of data, large data, big data in various contexts. So what are the typical sizes we are talking about? Can you give a sense of the sizes of these data?
Good question. So really no limit on size. We're seeing a lot in terabytes these days. And in an architecture like this, it's all part of that same scaling strategy. So if you're holding your data in memory, you're limited a little bit in terms of just how much RAM your machine has. So if you're looking at EC2, there are very large instances now where I can pull in a ton of RAM on a single box at not insane costs. But you don't even need a machine with very much RAM here. You can also sort of scale wide if it's more cost effective to use instances with smaller amounts of memory. But providing you can partition the data on which you're doing your compute, there's really no limit on the amount of data you can hold as long as you're comfortable scaling as wide as needs be.
Very good.
So the architecture that I've just outlined in the past slide really meshes well with a microservices architecture. The microservices paradigm really involves writing functions or business functions around state that's private to that function, and that state is only accessible over messaging. So these architectures tend to scale very well for the reasons that I talked about before. Once you keep your data private to a particular service, you eliminate any of the contention on updates. Your messaging fabric's going to serialize requests to your application, and you don't have contention on any piece of state. So you can take any microservice with its own private state, you can partition the data on which that microservice is working, and really scale up and use your hardware most effectively. So applying microservices to machine learning, when we're talking about the use case of trying to collect a bunch of data that we want to feed to our models, our data scientists have told us that we need data from some other piece of the organization. It fits really well into a microservices architecture because I can then just develop a pipeline where I go and progressively am collecting these variables that I need to feed to my machine learning model that's pictured here as another microservice, just in a pipelined or orchestrated fashion where I am going and picking up the data I need. And it also tends to be very efficient on the network, because as opposed to pulling down a bunch of data and aggregating it over the network, I can go aggregate, normalize that data at each service, and the output of each service is really just a few computed variables that I'm going to collect and send to my machine learning model. So microservices actually fits very well in the overall agility picture of trying to keep my organization's data very accessible to changing needs in what my machine learning models are going to want as their inputs. I can, at low risk, spin up a new service to capture data that I don't have in my organization, and as I have new models that need data, I can very easily incorporate into flows to go and pick up the pieces of data that I need. And so one might think that putting together a flow like this, where I've got to, let's say I need to get data from hundreds of microservices to feed my machine learning model, one might think that that would be very slow to do. But as long as our microservices are streaming these requests, modern messaging architectures like our Solaces, our Kafkas, they can do network hops, a message from one service to another in microseconds. And if we're keeping our data in memory, that's also going to be in microseconds. So you can actually string together a lot of services picking up data to feed our models in a very small amount of time, which is sort of counterintuitive. If you look at this kind of architecture diagram, I would think it might look slow initially.
Colin?
Yes.
So a quick time check. We're about 50% into our webinar, and we have an important question from Matt, who's asking, how does this architecture support the analytical load, considering that you are heavily partitioning the data?
So that's a good question, and actually dovetails well into this slide. So in an analytical workload where you're partitioning a lot of data, you at times need to join that data across partitions. So in that case, in a case where just a straight through processing pipeline is not going to work, microservices lend themselves very well to a sort of fork join approach, or you can think of it as an ad hoc map reduce type operation. So if I have a service that I want to bring online that's being fed by machine learning, and I need to assemble data from a lot of places in my organization, I can send out requests to the service that owns it, and that's maybe across multiple partitions of that service, to do some compute, do some normalization of that data, and return the data to be co-located by one sort of orchestrator service. So by doing that, I can do parallelized processing across the data in my organization, pull that data back together, do any join-related logic in one or more services here to fully assemble the set of variables that I want to feed to my model. But that is definitely a challenge to be considered, is when you scale out to achieve higher throughputs, you will be doing potentially some of this fork join type logic to achieve maximum parallelization while still being able to operate at high transaction volumes. So Matt, I hope that answers your question. You can perhaps refine it if there's more to be answered later.
Okay. And another related question from Shadi is, how often should the model be retrained in such a case?
So that's a great question as well, and it comes into the idea of monitoring the efficacy of your machine learning models at real time. So potentially you want to be looking at just how accurate or how good those results are in terms of driving the business goal that you're looking for. So in some cases it'll be an offline workload, maybe batch workload in the background that if we're doing fraud detection, for example, would be validating how well the model's doing. And you will want to continually evaluate that over time because spending patterns might change. And so customers that we work with update their models, maybe 6,000 times a year. So it can be a very frequently changing model, and we want to have an architecture where it's easy to push new models into production and be able to do A/B testing on them on live production loads, before actually making them live. And microservices work really well for that too, because I can have a new model that I'm about to promote into production, running off of real production data and evaluate how well it does in real time. Which is also a nice lead into just thinking about in a microservices architecture, whatever framework you might be using. Think a little bit carefully about what encodings you're using, because microservices are talking to one another via messaging, and each of these services has its own independent development lifecycle. So as I'm upgrading a service to version 2, but I've got a service still on version 1, I need to make sure that version 2 can still understand the requests that are coming to me. So think a bit about just what encodings you're using and how efficient they are in terms of serialization, deserialization, and whether they evolve gracefully over time. And you'll need to have some sort of agreement within your organization on when you can retire certain types of requests or operations for any particular microservice. So one needs to be very careful about the APIs exposed by any particular microservice and who's using it before it can be retired. So this one also touches a little bit on how often a model needs to change. When we're thinking about our transaction processing and the business logic that we're deploying, we need a framework that's flexible enough to not just assemble the vectors that we're going to feed to our machine learning models, but we also, while we're working on that data, are doing just our regular day-to-day business. So what we want to avoid is having to iterate through a ton of data one time for machine learning and then again to do our business logic. So you just want a framework that can do both. And probably you should be careful to introduce some sort of sanity checks, whether it be just regular business logic or some sort of rules processing, to again just keep tabs on the potential for your model being either maliciously compromised or degrading over time. So I like this example on adversarial inputs where you can feed a picture of this panda into an image recommendation model, and by just perturbing the pixels a bit, you can make the model think it's a given. So sometimes these things are not very obvious. Machine learning models are in a little bit of a black box. So having some sanity checks and leaving capacity to do that's very important. So, and we've, through questions, I think already talked a lot about just making sure we're monitoring our models and how well they're doing versus our business goals. But one thing to think about in terms of doing that is we don't want to necessarily compromise our transaction processing performance. And we should be thinking about ways to get all of this transaction data that we're amassing in our transaction plane out into our back end so that it can be monitored, one, for how well the model's doing, but also for future training and model refinement. So any more questions on that? I'm going to talk just 2 or 3 slides on how the X platform handles some of these, but before we get into it, any questions on this?
We have one question from Abhijit, who's asking, would the data replication also need to be in real time if you are talking about nanoseconds processing time and if the application crashes?
Yes, it does. And the replication piece is a very sensitive one. If done wrong, you're not going to get the real benefits of memory-oriented or shared memory function co-location. because if you replicate that data and you want it to be consistent in the case of a failure, if you do that in a synchronous fashion, you haven't really done much better than using a shared storage technology or a non-co-located storage technology. So I'll talk about how we handle that one in the X platform in a couple slides.
Okay, and one more question very quickly is from Chanavir. What parameters do you use to partition data in your approach, like plan for scaling or whatever? Are these simple size-based partitions, for example, 0.5 gigabyte per partition type of thing approach?
So it depends. In terms of partitioning, there are a couple of different dimensions you may need to scale on. So if your business logic is very computationally intensive, it might be that you need to scale on CPU. If it's very data intensive, you might need to be scaling on just memory footprint. Or if you've got really large requests, it might be on sort of the network capacity for any of the particular requests coming in or out. Under the covers in our platform, at least, the way that we make scaling transparent is typically a request. We talked about an example earlier of a customer management application that is scaled on a customer's last name. For us, we would look into a particular request and see that last name and route it to the particular partition based on a configurable routing function. So for us, we're trying to make it very transparent how a request gets to the particular data partition. But it's certainly a somewhat complex one. You just need to make sure that it's very flexible in terms of being able to repartition, rebalance. So there are some under the covers complications to think about when doing that. So hopefully that answers that question.
Right.
So the X platform mentioned at the top of the talk, what we're really about is handling the intersection of compute, messaging, and data into an easy-to-use programming paradigm. And when you're talking about consistency across failures, it's really important that you handle both the messaging piece and data piece in a holistic fashion, because it's very easy for those two, the messaging stream and your data stream, to get out of sync in the face of a failure. So that's what the X platform aims to relieve application developers from having to think about. So we do that in two main ways in the X platform. One is we give you modeling tools to allow you to model your application data or state. So we will generate plain old Java objects that you can use and interact with while processing your requests. And all of those live in memory, and the platform gives you the illusion that that memory is durable. So under the covers, we're replicating any change, any sort of field on a message that you touch transparently to you as an application. So we're replicating to a backup instance. And the other piece in which we're helping manage your messaging is we'll take care of the routing under the covers. So when you're partitioning your data, we're going to route those messages to the correct partition, so sort of transparently to application logic. And we do that in a means where we call messaging fire and forget. So when I send a message out of one of my message handlers, I can be assured that it's going to reach any downstream participant in a once and only once fashion, even in the face of failures. So by combining these two concepts of in-memory durable storage and exactly once messaging, we're just providing you with an environment where any changes you make to state is completely consistent with the messaging. And that makes for a very productive programming model. And so under the covers, it might not come as a surprise that it looks a lot like the architectures that I've been talking about so far. But the general flow in an X platform application, this is an order processing application partitioned across an order ID, where we're routing requests to a particular primary instance. We route that message in a single-threaded fashion to one of your business logic handlers, just based on type. And you do your processing we're going to replicate in a pipelined but asynchronous fashion to a backup instance. So that's very important in that you can move on to processing the next request before receiving acknowledgement from the replication backup. So we can do that business logic processing in a completely non-blocking fashion, and that gives you very high throughputs per application instance, transparently to your application code. So that's really where a big piece of the innovation in our platform comes in. Makes it very simple to partition application state, route requests to it, and have those requests be processed in an exactly once and reliable fashion without risk of there being any availability issues when an application instance or machine crashes. So applying a machine learning workflow on the X platform, it's very much a microservices flavor of solution where all of the data that you need to collect for a machine learning model is held in various microservices, and the microservices states partitioned. Each of those partitions is running a backup instance for high availability. And the entire processing flow is asynchronous and non-blocking end-to-end, which allows us to do very high throughput transaction processing at low latency. So the big thing that we're very sensitive about is never blocking anywhere in this transaction processing flow. And you can do that if your data is co-located with your function and you don't have to do any synchronous callouts to a backup instance. So that's the X platform, microservices and machine learning in a nutshell. I'm going to move on to talking about a fraud detection example, but any questions on that before I go on?
No. I think a quick time check, we have about 15 minutes or less to wrap up.
Okay, only a couple more slides.
Okay.
So,
That's good.
So looking at building a fraud detection workflow, this is an application that's available in our GitHub repository, a reference application, and it's a nice example of machine learning because it's a very simple, in some ways, use case. But essentially, I have a authorization request comes in that has a card ID and a merchant ID, but I don't really know much more about that request up front. So I need to assemble some data about the cardholder, assemble data about the merchant, and then finally, once I've figured out who the customer is, that customer might have multiple cards, go through that entire customer's transaction history, do some business logic on it, just my own rules-based processing, and off of that entire transaction history, assemble, I think in our model, about 100 variables to feed to a machine learning step. So in a microservices architecture, that would look something like this. Our authorization request comes in. I have just a card ID that I want to map to a user. So this card master service is sitting here partitioned, and each one just has a map mapping that card ID to a customer ID. So I can find the customer and my customer profile information to pass along in the pipeline. So first step, I locate the customer, enrich the request with the customer details, send it onto this merchant master instance, which does the same thing for the merchant ID that comes in the transaction. Again, just a map partitioned across multiple instances. Look up merchant details and enrich that request more. And finally, with my fully enriched transaction request, get to the instance that's holding all of my customers' transaction histories so that I can, in memory, go through and iterate that transaction, computing variables that I need for my machine learning step, and doing any fraud detection checks that I'm going to do in code. So once I've assembled that vector, we have a fourth microservice that's running TensorFlow, and that takes the vector of variables that I've assembled, feeds it into TensorFlow, and TensorFlow is going to spit out a result of whether it thinks the transaction is fraudulent or not. So what's nice about a microservices architecture is that we can scale each one of these services by the right dimension. So for example, the processing requirements on this map lookup are very small, so I might not need to scale this very wide at all. The amount of data that I'm holding isn't very much. But the credit card transaction history, that's going to be huge, and I might want to scale that much wider. And the amount of business logic that I'm running on it is also more intensive. So I can more effectively cost out my solution, knowing that I can scale each of these services in the correct fashion. And TensorFlow, for example, I might want to run on a machine that's got GPUs installed. So I can really deploy out and scale cost effectively. So we ran this flow in our lab across 3 machines, and you can see by virtue of the state being held in memory, each step is really happening in microseconds. So the first order of hop, 11 microseconds to look up the credit card details, another 13 microseconds to look up the merchant details, and then a bit more processing intensive to do the scan of 2 years of transaction history and the TensorFlow models not running on GPUs. So another 100 microseconds for each of those steps. And while running within 2 partitions, we can absorb 7,500 transactions per second at an end-to-end latency of 1.2 milliseconds. So the rest of that time is spent on the network going through a Solace router. So it's very easy to kind of scale these things out, achieve very high throughputs at really reasonable latencies. And looking through 2 years of transaction history, I can get an authorization response back to the point of sale terminal in just a millisecond. So that slide says the same as the last slide. So it's just sort of saying what we've seeded there. So you can imagine scaling this out more partitions than just the 2 that we deployed there to actually do a full production size authorization flow. But the throughput that we're achieving here is pretty typical of a big transaction processor. 7,500 transactions per second is about normal. At peak loads, they can go up to 30,000 around Black Friday and such. So I went a little bit over there, but Sabu, I'd like to pass over to you if you've got anything else to add.
Very good. Thanks, Colin. We have a few questions queued up already. And I would encourage the audience to type in more questions. We'll take those. We'll answer a few questions or take up a few questions for answers in a few minutes. But before that, I want to give a brief overview of Synerzip. So thanks, Colin. So this is my contact. I can be reached. I'm based in the Bay Area. And I help when Synerzip work with customers to do software product development in various technologies. Next slide, please. So about Synerzip, we are a 14-year-old company, well-established company. We serve typically venture-backed small to medium-sized businesses to do outsourced product development. We understand them well, and we serve them with a delivery model tailored for each. We speed up product development product delivery roadmap by working alongside clients' product development teams. We'll be able to fill technology gaps, skill gaps, if any, as required. With on-site and offshore software product development model, our clients benefit from speeding up of products from time to time and bring the product to market with significant cost savings. Next slide, Colin. So this is a typical representative of the client logos that we had served in the last 14 plus years. We've been in existence, and every customer we strive to be a reference customer. We take care of them well, put together very tailored teams, and this list has been growing. We find it a challenge to fit more and more logos into this slide, so we need to spread it out into more slides in the future. Next slide, please. So these are some of the ways or channels you could contact Synerzip on Twitter, LinkedIn, Facebook, other social channels. So feel free to reach out and contact us. Next slide, please. Okay. a peek into the next webinar that's coming up. That's again going to be a very technical webinar. In the client side, developing applications, there's always a struggle as to which technology do you use or you select, whether you do native on the mobile and website, or use Angular, or use frameworks like Angular or React, and there are a lot of other frameworks that are coming in handy. So we'll be talking about this from a couple of architects at Synerzip. So this is going to be a very important webinar, and you'll learn a whole lot of things in our next webinar. So with that, I would like to take up a few questions. So, the question from Lynn is that you mentioned about machine learning models and all that, Colin. So, would you be able to define clean data? We have heard of garbage data on one side and pristine data on the other side, other extreme. So, when you talk about machine learning models, would you be able to define clean data in your own world as to how we are going to take it up and process in the various microservices applications that is being developed in X?
Yeah, so I think that comes in a lot during the training phase, where I'm trying to sort through unstructured data and normalize it to feed it to a machine learning model such that it doesn't skew the results. So I typically want to normalize all of my variables on a sort of 0 to 1 scale so that it doesn't outweight the training algorithm. So in the training phase, a lot of the dirty data pieces would be trying to get a bunch of unstructured data that maybe I don't own, not to act as outliers that throw off the model results. When taking a machine learning model to production, a lot of times, if data is coming from an external source that I don't own by my organization, in our platform, part of that cleaning process would be ingesting that data from that other source, cleaning it on the fly, and holding it in memory as a proper microservice. So that ability to ingest new data that's coming in and exposing it to a machine, make it available for machine learning model in its clean and structured form is definitely a part of the workflow in terms of feeding the microservices you're developing.
Okay, very good. The next question from Alex is, are we talking about streaming data or batch data or both in the X platform processing these?
Very much streaming data. So for the types of performance demanding applications that we're talking about, it's low milliseconds or microseconds that we're trying to achieve, which you wouldn't get out of batch. We do have facilities in the platform that allow you to do some back-end processing that's more batch-oriented, but those results are not going to be the results that are going to come out real-time and feed front-facing applications. So we're very much about moving away from the batch processing paradigm.
Okay, thank you. And one question from Helen is the data coming from a relational database source, or could they come from any type of data source?
We work with a lot of customers that have data in relational databases. The typical approach we take is to ingest that data into an in-memory microservice that would then allow you to operate on it at real time. So we have features in the platform that allows you to load that data into memory, fronting the database, and then siphon that data back out in a consistent form via change data capture, but asynchronously, so that the database doesn't become a bottleneck. But typically for the workloads that we're looking at, a database is going to be too slow.
Okay, thanks, Colin. And one last question that we can take up, we are almost up against our time, is can the microservices be written in any full stack languages in the X platform, or do we have any restrictions in the language selection for writing microservices?
It's a good question. So any language that can run on a JVM is what we would be limited to. The training of models, any language you can use. So for example, any machine learning framework you're using can typically be run on Java in production. So a lot of times we see data scientists working in non-Java stacks. But the model that gets deployed to production would be something that can run on the JVM. So training, typically less Java focused. For us, it's mostly Java or Scala.
Okay. Very good. Thanks, Colin. So almost we have reached the end of this webinar. I want to thank you, Colin, and Jill for coordinating and putting together this webinar, and I really appreciate it. So we encourage early registration for our next webinar. That's going to be a hot topic, as I said, Angular versus React. So I would request everyone to go to Synerzip website and make sure you register early and put it on your calendar so that you don't miss it out. That's going to be an absorbing topic as this one was. So once again, thank you all for attending the webinar, and we'll catch you in the next month's webinar. Take care, everyone.
Thanks, everyone.